10 minutes before, Oscar? Yeah. Okay, so yeah, here we go. Thanks to the organizers for having me here, and for all of you, the organizers. Rafael, thanks for having me here. It's late and I'm very jet lagged, so please ask me questions during the talk. Okay? Help me keep awake. And the other thing, I changed the topic. I decided to talk about some recent results on twisted bilayer graphene. You see, of course, very related to things you heard earlier today and things that are going to be discussed later in this conference. Okay, so this is my plan. So I'm going to talk about twisted bilayer graphene, familiar to probably all of you, and this tension that was discussed actually earlier today, how to think about the system. On one hand, we know that this is a system of topological flat bands. And on the other hand, we have very strong correlations that tend to localize electrons, and there's an intrinsic tension between these 2 points of view that came up very early in the discussion of the system. And what I'll discuss is, I think recently over the last several years, there's been very nice progress, both theoretical and experimental, in reconciling these 2 points of view, and this actually led to a new theoretical framework of how to deal with a class of strongly interacting systems that is very suited for this kind of system. Okay, and in particular, the progress is in dealing with intermediate temperature regime in this system. This is the so-called flavor incoherent regime, where the flavor, the spin, and the valley are thermally disordered. Okay, so. Right, so we get these flat bands in twisted bilayer graphene. Now we know of several different ways of getting flat bands in condensed matter systems, as was discussed actually a little bit earlier today. If you just put electrons in a very deep lattice, for instance, you'll trap every electron. The wave function would be very localized around the lattice site, and then if the electrons interact, you might get an insulator with some integer number of electrons per unit cell. Okay, and the flat would be the band would be very flat, just because it's very hard to tunnel between one lattice site and the next. A totally different way to get flat bands is to apply a magnetic field in a two-dimensional system, and we get Landau levels which are completely flat. But of course, the origin of these flat bands is completely different from the origin of this very deep periodic lattice. Here, it's really an interference effect. The wave functions are actually strongly overlapping. You can't localize completely electrons in a flat band in a Landau level, and the topology, of course, has all kinds of physical consequences that we're familiar with. Okay, and a magic angle twisted bilayer graphene does exhibit these extremely flat bands, and the question is, how should we think about these flat bands? Okay, so are they of this class, sort of localized electronic orbitals, non-overlapping, strong local interactions, or topological extended bands with wave functions that have to overlap with each other? So yeah, so if you think about the system from either point of view, that has very different physical consequences, and the question is what's the correct point of view? Again, the interesting thing is that this system actually exhibits features that mix both what you expect from either of these points of view. Okay, what was noticed quite early on is that these bands in magic angle twisted bilayer graphene are topological. So they're topological bands in the sense that there's no choice of exponentially localized Wannier basis for these pair of low energy flat bands. It also preserves all the symmetry of the system. So this is the so-called topological obstruction. That means that this system really cannot be described in terms of a basis of tightly localized wave functions around every lattice site. Okay, and why is where is this topology coming from? Most of you are probably familiar with this, but I'll show it briefly anyway. Okay, so if you think about where these flat bands are coming from, okay, you think about their origin. So you see that they're very flat, but if you just plot them on an expanded scale, they actually touch each other at 2 points in the mini-Brillouin zone. And these Dirac points are protected by symmetry, specifically by the combination of C2 and a C2 rotation around the Z direction and a time reversal. And there is a form of band topology which is actually protected by this C2T symmetry. Okay, you can understand that as follows. A Dirac point in a C2T symmetric system has a sense of chirality, and this is very, very familiar from graphene. So every Dirac point has a winding number associated with it, and this is what stabilizes it. And the two Dirac points in graphene have an opposite winding number. So for instance, if you apply a very strong strain, if you deform the lattice, the Dirac points can move, merge, and gap each other out. In magic angle twisted bilayer graphene, the two Dirac points in the mini-Brillouin zone in a single valley originate from the two Dirac points of graphene, of the two layers of graphene from the same valley. And it's sort of intuitive that they both have actually the same winding number, not opposite winding numbers. The ones with the opposite winding numbers live in the opposite valley. And this is why they actually cannot annihilate. So this touching of the two bands is actually protected because of this topological property of the two Dirac points. So this is one manifestation of this form of band topology. Okay, and this has really been discussed very early on. So the upshot of this is that we get these two flat bands. They really are flat because of a very subtle interference effect. They're topological, and therefore we should think about them as some kind of Landau levels. They're really in this dichotomy that I presented before. You should really think about these as some sort of generalized Landau levels. And if they're Landau levels, you turn on interactions. We know quite a bit about what happens when you have electrons in a Landau level that are strongly interacting. One of the first things that you might expect to happen is that if you partially fill these bands, you'll start getting generalized ferromagnetism in spin, valley, or orbital space. Okay, and the reason for that is very familiar. Quantum Hall ferromagnetism is basically maybe the best understood ferromagnetism. You just have flat bands, no kinetic energy, and you can gain a lot of exchange energy by polarizing. Okay, so you can polarize in spin or valley or both. What type of a flavor order you would get can depend on all kinds of details, but this is what you expect, some kind of generalized ferromagnetism. Okay, and an early measurement that was done in Shechalilani's lab at Weizmann was actually interpreted in this way. So what was measured is the electronic compressibility, the inverse compressibility, d mu dn, as a function of electron density. Okay, and so this is as a function of filling factor in the Moiré unit cell between -4 and 4. Okay, and it turns out that the inverse compressibility does not go smoothly from -4 to 4. So first of all, this is inverse compressibility. A peak here means a gap. Okay, a gap would look like a delta function peak, like a very sharp peak. It's a jump in the chemical potential. So this is exactly what you see at -4 and +4. So this is basically when you completely empty or completely fill the flat bands. This is what you expect, but in between you see this sequence of features that appear. Okay, so you see this the softer peak close to charge neutrality point. So this is not quite a gap. Okay, maybe exactly at charge neutrality there's an additional sharper gap, but this kind of broad feature is not a gap. It's just a reduced density of states, and yeah. This is real. This is a little bit of a matter of definition. So, yeah, what the experimentalists define as the inverse compressibility, dBUDN, is really the capacitance to the gate minus the inverse capacitance to the gate minus the geometric capacitance. Okay, this thing can actually go negative. Yeah. You basically subtract some reference. Yes, the system is thermodynamically stable, absolutely. Okay, So the observation was this sequence of jumps of the inverse compressibility that happens close to every integer. This was interpreted in terms of a very, very simple model. You have a Dirac dispersion. So at charge neutrality, you have a Dirac dispersion. This explains this peak in the inverse density of states. And then as you fill the system, at first, the system is flavor symmetric. So you fill all the 4 flavors, spin and valley, together. At some point, you exceed the Stoner criterion. The system tends to break the symmetry. So you fill 1 flavor completely and empty the other 3. It turns out that they tend to reset back to the vicinity of the original Dirac point. And then you just repeat this process again. And from the simple model, if you calculate the inverse compressibility, you get this sequence of a so-called cascade transitions where the flavor symmetry gets successively broken, and they tend to happen close to the integers. Okay, so it turns out these transitions are not pinned exactly to the integers. They're not pinned exactly to the integers. Also, the experiment, they move a little bit with temperature or magnetic field. Okay, but this interpretation seems to support the picture that flavor ferromagnetism is the sort of the driving force in this system. Yeah. Between, yes. Yeah. Yes. Yeah. 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 So in fact, when you start digging a little bit deeper into it, there's no reason in the experiment for to have an exact particle symmetry. Okay, so there are all kinds of effects that actually break particle symmetry. Okay, but particle symmetry is there approximately, but it's definitely not an exact symmetry of the system. Okay, so yeah, so soon after this, it turns out that things are actually more interesting. Okay, so the system actually is not just a sort of a version of a quantum Hall ferromagnet. Okay, and the way at least we noticed this very dramatically is by looking at the system at finite temperature, looking at actually what happens to these cascade transitions as you raise temperature. And it turns out that they evolve in a very surprising, what I found very, very surprising way. So this is a measurement, quite recent measurement by Dima Ifetov's group, but there are actually many measurements earlier that show the same thing. So this is now looking at the resistance, not compressibility. Okay, but you still see these cascade transitions that happen close to the integers. And what was noticed is that if you track what happens to these transitions when you raise temperature, they actually move in a way that what you thought was the ordered state is actually expanding when you raise the temperature. Okay, so this means that what you would have labeled the ordered side actually has a higher entropy than the disordered side. Again, we named this the Promanchuk effect. It's an analog of the Promanchuk effect that happens in helium-3, where you heat up and the solid is expanding relative to the liquid because the solid has a high spin entropy. Okay, and you can actually go further and actually measure the electronic entropy as a function of temperature and magnetic field. Actually using thermodynamic relations, but what the quantity which is actually measured is the electronic compressibility, and you use a Maxwell relation to extract the entropy. And it turns out that indeed the entropy close to charge neutrality starts quite low, but it increases very rapidly, and by the time you are close to nu equals 1, there's a very large electronic entropy of the order of 1 kb per Moiré unit cell. And moreover, this excess entropy is very sensitive to in-plane magnetic field. So this means that it has a spin, at least a big part of this entropy has a spin origin. It gets polarized when you apply an in-plane magnetic field, and the in-plane magnetic field that you need to apply depends on the temperature, exactly like you would expect from the spin of a localized electron, basically. Okay, so a very simple way to interpret this phenomenon is to say, well, twisted bilayer graphene actually should be thought of in terms of a Hubbard model. Okay, you just have localized electrons, one orbital or two orbitals per unit cell, and there's a very strong repulsion. So if you're putting electrons in this lattice, you want to have some integer number of electrons per unit cell, but the energy doesn't depend on the spin, say, or the valley of these electrons. And if you raise the temperature just a little bit to destroy any order that might be there at zero temperature, these spin and valley moments would fluctuate very strongly. Yes. Yeah, so in this particular experiment, they didn't have an out-of-plane field. So the experiment, to the best of my knowledge, was not done. Of course, there would be an orbital effect. You sort of expect the reduction of the entropy to be greater. That was actually seen. So an analogous effect to this was seen in a Morel system. And indeed, that's what you see. You see that you suppress more of this entropy if you apply an out-of-plane magnetic field. Yes? Yeah, so these cascades disappear somewhere between 30 and 50 Kelvin, depending on... No, but you sort of see the cascades gradually just fading out, and by about 50 Kelvin they're gone. Okay, so yeah, so the question was how to reconcile these two apparent observations. Okay, we have topological bands. We believe we do have some kind of spin and valley order, ferromagnetic or nearly ferromagnetic order at zero temperature, but we just raised the temperature just a little bit. Okay, so in this experiment, 10 Kelvin, these phenomena are observed even at lower temperatures, maybe 5 Kelvin, and the system behaves as if there are localized moments coming from local electronic orbitals. Okay, and I think a very important step towards resolving this puzzle was made by the introduction of the so-called topological heavy fermion description. Okay, the first hints came both from experiment and from theory, okay, both in STM and in band structure calculations. What you observe is that if you look at the wave functions of twisted bilayer graphene of the flat bands, they're actually not homogeneous over the Moiré unit cell. They're actually very, the charge density of these wave functions is actually very peaked close to the AA regions of the Moiré unit cell. Okay, so it's very natural to guess that maybe you should be able to describe the flat bands, or at least most of the flat bands, as in terms of localized orbitals that are sitting at the centers of these AA sites. Okay, and this is exactly what Sung and Berevik did. Okay, so they realized that you can actually introduce a basis which spans almost the entirety of the flat bands, which is just made out of Gaussians that are localized on the AA sites. Okay, so this is actually the overlap of this basis with the flat bands. You see that it has a very large overlap almost over the entire Brillouin zone, with the exception of a region around the gamma point where the overlap actually goes to zero. It goes to zero for a symmetry reason. So these wave functions, these localized orbitals that are centered at the AA sites, have the wrong symmetry to describe the Bloch wave functions of flat bands exactly at the gamma point. So there the overlap with this basis goes to zero, but away from the gamma point the overlap is very large, so they span almost the entire flat band. And the idea is to use this as a basis that has basically two types of orbitals. It has localized orbitals that sit on the AA sites that are describing the flat bands almost everywhere, and then the two pairs of remote bands above and below that carry the missing weight, basically. Okay, so this is as formulated as just a change of basis, but it turns out to be a very useful basis to describe the system. Okay, so the idea would be okay, so this gap is large in practice. This gap can be 50 millivolts. But because most of this band is actually described by these very localized wave functions, maybe they can give rise to the localized behavior, even though overall the band is actually topological and cannot be spanned completely by these completely localized orbitals. Okay, so here's some evidence for sort of a localized moment or Hubbard-like behavior in magic angle twisted bilayer graphene, okay, in the intermediate temperature regime. So it turns out that at charge neutrality, if you assume perfect particle Hall symmetry, you can actually solve the problem using quantum Monte Carlo. There's no sign problem. Okay, and we did that. Okay, so but we're doing this exactly at the charge neutrality point at nu equals 0. For instance, here's the entropy as a function of temperature. Okay, so this is for different system sizes, just to show that the results don't depend much on a system size. Okay, so at very low temperature, the entropy is low. We understand what's going on there. The system is actually flavor polarizing into a KAVC state. Yes. Yeah, so the model we're simulating is we're taking the two lowest energy narrow bands, projecting long-range Coulomb interactions into these bands, and then just solving the problem. Now, this is no. So this is actually done in momentum space. We're not assuming any real space structure. Okay, the only structure we're assuming is the structure that's coming from the wave functions of these bands. Okay, and this is close to the magic angle. The bands are not mathematically flat, but quite flat. Yeah. 6 by 6. Yeah. 6 by 6. It's a 2D. Yeah. Yeah. Yes. Yes, yes, yeah. We can go up to 12 by 12 in this calculation. Yeah, in a moment I'll show you slightly bigger systems. The entropy, we're interested in this intermediate temperature range where the entropy, where nothing really depends much on system size. Okay, so the observation that I find kind of striking here. Okay, so at very low temperature, you go into an ordered state. We can discuss what that ordered state is, but the entropy is becoming very low. Okay, and then there's around 10 Kelvin. This is basically where the correlations of this ordered state become very short, less than 1 unit cell, and the entropy rises very sharply. But then there's this intermediate temperature range where you see this this knee or this step in the entropy. Okay, this is a range maybe between 15 and maybe 40 Kelvin, where the entropy seems to plateau around this dashed line. Okay, and this dashed line is just H choose 4 times KB. Log of H choose 4 times KB. What is that? That's exactly what you expect if you just had a Hubbard model. Okay, so if you suppose you had a Hubbard model, there are a total of 8 states per unit cell. Okay, 8 states because there are 2 orbitals, 2 spins, two valleys. Okay, and if you have a very strong on-site Hubbard U, that would like to quench all charge fluctuations. So we have exactly 4 electrons in every unit cell, but internally the flavor can fluctuate. Okay, and you have a total of H choose 4 possible states for every site. So this is exactly the entropy that you expect when the temperature is bigger than any exchange scale between the sites, but much smaller than U. So the charge fluctuations are quenched. And in fact, this black line over here is just what you would expect for such a one-site Hubbard model, basically. Okay, so with a U scale that is just fit to match at high temperature, the U that you get out of this fit is maybe 30 millivolts. Okay, but let me just emphasize the model that's being simulated is not a Hubbard model, right? It's just the flat bands with a long-range Coulomb interaction projected to the flat bands. Okay, so that's one observation. So this kind of sort of localized electron behavior does seem to emerge in magic angle twisted bilayer graphene in this model. Okay, the other observation is if you look at the spectral function of the electrons at different temperatures as a function of K, okay, you can calculate that from the same calculation. You have to do analytic continuation, so that's not as robust as a thermodynamic quantity like the entropy, but you can do it nevertheless. This is what the spectral function looks like as a function of K. This is at low temperature, okay, over here in the ordered state. The state that you get here is the so-called KIVC, or Kramer's inter-valley coherent state. It's a particular form of a flavor ferromagnetism, and you get a fully gapped spectrum for the electrons. But if you raise the temperature to this intermediate range, where you get the plateau, you see that in most of the Brillouin zone, the spectrum is sort of similar to that of the ordered state. Okay, it looks like just two quite flat bands, plus and minus basically u over 2. Okay, so this this value over here basically corresponds to half of the u that you would fit here, except close to the gamma point where there's a gapless, there's a band touching. These two bands actually touch. Okay, and this form of the spectral function was actually obtained in many different calculations in this disordered regime, in the flavor incoherent or flavor disordered regime. Okay, so it was obtained using a DMFT by several groups. Okay, so Lenny will probably talk about it later in the conference. What the observation was in all these calculations is that you get mott-like bands over most of the Brillouin zone, except that in the vicinity of the gamma point where you get the semi-metallic behavior instead. Okay, so this is so the colors are not very good, but this is a calculation. This is actually using the topological heavy fermion basis, but that's just a basis. So right, the last thing I wanted to show is the same thing can be actually derived analytically, and I'll discuss that more in the next slide. Yeah. Yeah. Great question. Yeah. So yes. So right. So what it means is the following. So you're absolutely right. There's no such thing as a gap at finite temperature. Okay. So in principle, the spectral function is non-zero everywhere here. It's never zero. Okay. But I can still take a cut and ask: do I get two peaks at plus or minus e, or do I get one peak at e equals 0? This is the criterion I'm going to use. Yes. Okay, so you're absolutely right. There's no such thing as a gap at finite temperature. The system is never gapped at finite temperature. Okay, but you can define. You can use the definition that I just mentioned, or you can just wake a physicist in the middle of the night, show them this picture, and say, where's the gapless point? Okay. Yes. Yeah. True. I'll actually explain where. Yeah. I mean, the yellow line. Yeah. Let me say that the yellow line is just where the peak in the calculation is. It's just but I think it would work without the yellow line. Yes. Yes. Yes, yeah. At the gamma point, not away from the gamma point. Yes, yeah. That's the phenomenology. Absolutely. Yeah. Yeah. So So it's a good question. Okay, within Hartree-Fock, as long as you have, if there's the two narrow bands are isolated from the remote bands, you have to have a broken symmetry to open a gap. Okay, you cannot separate. That's really the band topology. You cannot separate these two Moiré bands without breaking some symmetry. That's true within Hartree-Fock. It turns out that it's not quite true for a strongly correlated state. You can actually think about strongly correlated states that don't break any symmetry, but at 0 temperature gap these two bands. Okay, but this is definitely not what's going on in this calculation. In this calculation, there's a broken symmetry. Yeah. Yes. Yeah. Yeah, so it turns out that in this calculation, the symmetry which is broken is actually U2 cross U2. So it can only be really broken at 0 temperature. At any finite temperature, the finite correlation length, but that correlation length is huge, all the way up to around 10 Kelvin, where it shrinks very rapidly and becomes of order 1 lattice constant. Yeah. great question. Yeah, yes. Yeah, yeah. Yeah, I'll show you in a minute. Okay, so yeah, so but let me just say, okay, this calculation was done by projecting. That's just numerically easier. There's no sign problem even if you don't project, but the calculation is much more demanding. We haven't done that. The DMFT calculations don't project. Okay, so all of these, you actually see the remote bands in the calculation. Okay. So now what is this? This is what I'm going to talk about for the rest of the talk. It turns out that in this flavor incoherent regime, you can actually make a lot of impressive analytic progress that's been realized very recently. Okay, and you can actually derive this kind of spectrum analytically. Okay, so this is a paper by Patrick Ledwith and collaborators, and there's a accompanying paper by Hu and Song and Bernevig that use a different technique to derive basically the same results. Okay, so what you do here is you basically you use as a theoretical control parameter the fact that almost all the flat bands can be described in terms of these very localized wave functions, except a small region in k-space close to the gamma point. Okay, and you use that as your control parameter. How much time do I have? Yeah. Okay. Yeah, good. All right. So yeah. So what I'm going to talk about in the rest of this talk is basically try to explain how to use this this control parameter to actually do controlled calculations, and moreover to improve on these results. So one thing which is curious about the results over here, okay, so you see that these lines are the lines that the peaks that you get in the spectral function, even though this is finite temperature, are actually very narrow. Okay, now the width that you see here is actually artificial. What you literally get from these calculations are delta function peaks. So you actually get that there are infinitely sharp quasi-particles, even though you're dealing with a very thermally fluctuating state. Okay, so this was very, very surprising to me when I saw this first. Now, let me just mention, if all the band was just made out of completely localized electrons, if you were really writing a Hubbard model, and this would be these would be Mott bands, you would actually expect these Mott bands to be infinitely sharp in energy. Okay, they're very ill-defined in momentum, but they're very sharp in energy. There's a very well-defined energy of U to add an electron, or minus U to take an electron out. Yeah. Yes. Yeah, so that's true. Yeah. So I mean, at the end, if you wanted to explain this in one sentence, I think that sentence is correct. Okay, now to make that into an actual calculation and to get all kinds of other features, okay, is harder. Yeah. Yeah. Yes. Yeah, so right. So yeah, for that we actually have to do a calculation. At least I don't know how to get that otherwise. Yeah. Okay, now let me mention that these two works actually took a very different approach to this problem. Okay, the work by Ledwith et al. Projected the interactions to the narrow bands, the same thing as what we did in the Monte Carlo. The work by Bernevig et al. Used the topological heavy fermion model that actually includes also remote bands. Okay, so but nevertheless, in the limit where gamma, where the hybridization is very strong and the gap is very large, these two produce the same spectrum. Yeah, so I'll show you experiment at the end. Okay, the answer. So in the Monte Carlo calculation, the gap to the remote bands was taken to infinity. It was projected. Yes. Yeah. Yeah. Yes. Yeah. Yeah. The ratio is sort of order 1. Yeah. I'll actually show you an experiment soon where okay, so what we'd like to do is basically to develop a technique where we can use this phase space parameter. Okay, the small parameter we're going to use is how much of the Brillouin zone is not described by localized Wannier functions. Okay, and we want to use that as our control parameter. We want to write a theory where we can calculate any physical quantity order by order in that small parameter. Okay, and this spectrum over here is nothing but the 0th order in that small parameter. Yeah. Yeah. Great. Yeah. So temperature is much smaller than U. Yes. But it's much greater. Okay, you'll see in a moment. It's much greater. So there's a dimensionless parameter, which is the size of this hole of the dispersion region, if you like, in the Brillouin zone to the size of the Brillouin zone. Okay, that parameter is called S. So the temperature is much less than U, but much bigger than S squared times U. Okay, and this is the regime where this calculation is justified. Well, yeah. So you know, in TBG, we're right. I mean, the U we think is 20 millivolts. Yeah. Right. Yeah. Yes. Yeah. Right. Well, I mean, at this stage, U is, you know, Coulomb. U is just given to us. Temperature can be smaller than U or bigger than U. That's just the. No. So this occurs in a whole range of temperature. Okay, in a broad range of temperature, as long as the temperature is much less than U. Okay, but there's also a lower limit on the temperature. Okay, so the temperature should be much less than U, but much bigger than U times S squared. Okay, where S is the ratio between this region in the Brillouin zone where the bands are dispersive to the size of the Brillouin zone. Okay, and that turns out to be a small parameter. It's not an extremely small parameter. It's maybe a fifth. Okay, but there's a fifth square there, and that gives us the range. Yes, yeah. Okay, so right. So we want to write a theory where this S parameter, this phase space parameter, sort of appears explicitly, and solve it order by order in S. Again, we use the topological heavy fermion basis. So we have two types of electronic states. We have the C electrons, which are very dispersive. They would form the remote bands. And we have the F electrons, which are very localized. They don't have a dispersion on their own, but they're hybridized with the C electrons through this matrix and also K-dependent hybridization gamma. Okay, and the only interaction we take for simplicity is just the on-site Hubbard U on the F electrons. Okay, in the Song and Bernovic model, there are other terms. There's also a repulsion between C and F, an exchange between C and F. We can add all these things perturbatively, but the U we want to treat non-perturbatively. That's the whole idea. Okay, so our small parameter is this parameter S. It's basically defined as follows. So it's a absolute value of gamma, the hybridization. For simplicity here, I'm using a K-independent gamma squared times the I at a frequency of order U. I is just the local density of states of the C electrons divided by U. Okay, so this is a dimensionless parameter, and it turns out to be equal to this ratio. Okay, it's gamma divided by V, which is the basically the C electrons are Dirac-like electrons. So this is the velocity of the C electrons times the size of the Moiré reciprocal lattice vector. Okay, so pictorially this is what it means. This is the dispersion where gamma is taken to 0. You get the flat bands, which are F, you get the very dispersive bands that have a speed of v star, and this S ratio is basically this part is basically this region in the Brillouin zone where basically where gamma, which turns out to be of the same order as u, is equal or less than the dispersion of the C electrons. Okay, so this is basically, yeah. Yeah, so yeah. Yeah. Yeah, so U actually cancels between these two. What happens is that the density of states of the C electrons here is Dirac-like, so this is proportional to U. So U actually turns out to cancel from this expression. Yeah. Yeah. Yes, yes, yeah. Yeah. Yeah, yeah. So yeah, so this is an on-site interaction, but independent of orbital, say, spin and valley. Yeah. Yes. Okay. Yeah. Yeah. So yeah. So right. I mean, here U is sort of yeah. I mean, this really could be any energy scale. I mean, it doesn't really matter because the cancellation is coming from the fact that the local density of states of the C electrons is linear in the energy. Yeah. Yeah. Okay, so this is really the proper definition of our small parameter. I'm basically out of time. Yeah, so I'll just advertise, and we'll happy to discuss more. But how do we actually use the small parameter to do calculations? Okay, so we use what's called strong coupling or cluster perturbation theory that was proposed early on for Hubbard model. It turns out that here, this is a very effective way to expose the role of this small parameter S. Formally, you integrate out, you start from the theory with gamma equals 0, and formally write an expansion in gamma. That expansion would be resummed. The results are not perturbative in gamma in the hybridization. You formally integrate out the F electrons, and you get the C-only effective theory that has n-body vertices, frequency-dependent vertices, that come from connected n-body correlation functions of the F electrons, all coming from a single site. So these vertices, these n-body vertices would be all local in space. Okay, and then you get an effective theory. The first term is simple. It comes from the Green's function of the F electrons, and it's a quadratic term in terms of the C electrons. This is the vertex I call gamma 1, but they're also gamma 2 and gamma 3 and so on. Okay, and then you want to calculate some property, for instance, the C electron self-energy, and you can write that as a loop expansion. Okay, so this would have all kinds of n-body vertices connected by loops of C electrons, and the upshot, and with that I'll end, it turns out that every C electron vertex comes with a parameter S squared. Okay, so the order S to the power 0 is the tree level, that's just the gamma 1, and this reproduces exactly the results of Ledwith et al. And Hu et al. Okay, so but you can improve on that by just going to higher orders, higher loops. That gives you, for instance, the width. Okay, so the first order here already gives you scattering. The C electrons all get a finite lifetime, as you would expect. You can calculate a susceptibilities, for instance, and you find a Curie-Weiss behavior of the susceptibility, meaning the system tends to order at low temperature, and you can calculate the ordering temperature and so on. Okay, so no. So they hybridize. So already at order S to the power 0, the F electrons hybridize with the C electrons. Yeah. So you're left with a C electron, which knows that they're F electrons. We integrated them out exactly. So now, even though we integrate out the F electrons, we can still calculate F electron Green's functions by adding a source term. And what we get is just a dispersion that looks like a hybridized C and F dispersion. Okay, if you look only at the C electrons, you would see a dispersion, but it has a large weight near the gamma point, and it just fades away. The weight just fades away as you go to the flatter bands of the flatter parts of the band. Okay, yeah, so if you ask me about experiments, I can talk about experiments, otherwise I'll finish here.
Rafael?
Can you tell me about experiments?
Yeah. I'll just show, I'll just show two very short slides. Okay, skip this. QTM, okay, Shachal Ilani's new technique. So he can measure the spectral function as a function of momentum, and he can do that at the magic angle, he can do that away from the magic angle. I won't go into how this works, but you basically take a cut in momentum space and just plot A of k and omega on that cut. And at the magic, away from the magic angle 1.2, this is what it looks like. This is as a function of angle, which translates into momentum in the mini-Brillouin zone. This is the gamma point, the k point, and the m point of the mini-Brillouin zone. Okay, so you see the BM dispersion. You see basically a gap closing at k. This is away from a magic angle. And this is what happens at the magic angle. Okay, so at the gamma point, it looks gapless, looks like there's a band touching, and away from the gamma point, there are these very, very flat bands, Hubbard-like bands. Okay, and you can actually extract numbers. Okay, so this is maybe plus or minus 15 millivolts, and the gap to the remote bands is maybe 60 millivolts. Yeah, the color map is confusing. White is basically very low, almost zero. This is saturated. This is high, this is low, high, low. White is the gap, yeah.
So before we move away from this slide, I'm gonna ask my question. Let's say you lower temperature in this experiment.
Yeah.
So according to this theory,
yes,
this should gap out.
Yes.
Does it?
Yeah, the experiment hasn't been done, being done now. This was at 4 Kelvin. Yeah, this experiment was done at 4 Kelvin. That setup didn't allow to go below. Now they're actually dilution experiments. Unfortunately, I can't tell you right at the same place in the same sample. This is what happens when you cool. So far, they've not seen a gap even at low temperature.
Because nobody else except for maybe Dima Efetov early on saw a gap at charge neutrality point.
Yeah, so
at low temperature from transport.
So Shachal actually saw a gap in some parts of the sample at charge neutrality. Unfortunately, he didn't publish it ever. But in incompressibility, most of the sample is gapless. But there are parts that are gapped at charge neutrality.
Because that could be an alternative explanation.
Yes.
All of this.
And that's this slide. Okay, so unfortunately, or fortunately, okay, so there's an alternative explanation that would give an extremely similar looking spectrum, but totally different state, which is if you just introduce a little bit of heterostrain. Okay, so this is actually our Monte Carlo calculation in the presence of heterostrain. What happens is that if you break C3 symmetry by heterostrain, the Dirac points of the unstrained system move. They move extremely fast. You really need a tiny amount of strain to get that, and they tend to stay close to the gamma point. So you get a spectrum that looks like this. For a totally different reason. This is a totally different state. Okay, this is a ground state essentially. Okay, this is very low temperature. This is not at 30 Kelvin, but the spectrum looks quite similar. You get very flat and gapped bands at maybe plus or minus 15 or 20 millivolts, and something that looks like a gap closing. In fact, there are two Dirac points here, but they're so close apart. You just smear it a little bit, and it would look exactly like that. So we don't know in the experiment whether we're looking at this or that. Okay, and we're actually trying to think about ways to tell.
Okay, I'll tell you a way to tell later. But okay, Paco?
Yes. Right. Yeah, gamma is the splitting to the remote bands. Yeah. I mean, the splitting to the two close bands, that depends on the angle. Okay, there's some angle where that actually changes sign. Yeah.
Okay, Andre?
Now, a question about theory.
Yeah.
You said that the results are non-analytic in gap. I presume that you're talking about frequencies close to you.
Yes. Well, yeah. So there are various points where there's a subtlety. I mean, one point is just the gamma point itself, right? So you're formally expanding in the hybridization, but you're trying to describe a state that has a gap. So yes, yeah.
So do we get any non-analyticity out of this? And
No. So the end result, we don't get anything. Yeah, what we get is like this. So first of all, we get a width. Okay, so the divergence that you get if you just do one loop when the frequency is equal to u, okay, you get formally a divergence. There's a way to resum that, and what you get is that there's just a finite width there. Okay, the width is scales like u times s squared times the number of electron flavors. Okay, and the other divergent quantity that you get is the susceptibility, and this is just coming from this Curie-Weiss behavior. Okay.
This calculation seems to be zero temperature.
Yeah, so the calculation is zero temperature compared to u. Okay, so you have to assume that T over u is very small, and then you do the calculation at some finite temperature. You get that the calculation should fail at the temperature scale, which scales like this.
Whether the question about thermal fluctuation that can potentially produce the gap right at gamma.
Yeah.
I don't see anything.
No, so yeah, so you know what this would say is that should happen maybe when the temperature becomes of order, the ordering temperature, but not above. Yeah, in fact, yeah, we can discuss it. This approach would tell you that the transition itself is actually very mean field-like. Yeah.
Raphael, please.
Now it's a real question. What happens when the K point is splitting U
Yeah.
is 5 times the splitting factor? So that you don't don't have a gap anymore in respect to forward. So what happens in this case?
Yeah. So you mean if I change
If you make the U be large enough that this is above the bottom of the remote bands, the K.
I see. Yeah, so this calculation doesn't actually project. So you can describe here a situation where there's kind of no, there's no indirect gap. There's nothing that goes wrong in this calculation. You would get some, presumably, yeah, you would get some extra width because you can scatter. There's more phase space to scatter, but nothing dramatic.
Yeah, Adi?
Is a simple way to understand how, when you raise the temperature, the quote-unquote gap closer, meaning the two maximum points in the spectral quantum get close to one another?
Yeah, so to study this entire crossover is something that we haven't done, but I think we know now how to do it using the same formalism.
Do you have a physical picture?
Yeah, so there would be a gap at the gamma point, which is coming from, is like a mean field gap. It's coming from the average order parameter, and I think this gap over here would just be proportional to the order parameter. Be proportional to the order parameter of whatever ordered state you have at zero temperature. I think so. I think this is what would happen. Yeah, what I've shown is all for nu equals 0. There's nothing in the calculation which forces you to be at nu equals 0. Yeah, yes. No, so that's actually interesting. In this limit where we know how to do the calculations and also where we think the material is, in the small s limit, the Kondo temperature would be much less than this temperature. Okay, so you'll get order. If you like, this is the usual competition, kind of Doniak phase diagram, competition between RKKY and Kondo. And in this setup, RKKY always wins.
Please do.
So correct me if I'm wrong. So you integrate out the heavy fermions.
Yes.
But the heavy fermions are correlated.
Yeah.
Because they have a view.
Yes.
So why do you call that RKKY?
Yeah.
In some sense.
Yeah.
Because it's still some correlated state
Yeah.
mediating interaction between the C. It's not uncorrelated.
Yeah. So I mean, right. I mean, I think the physical origin is RKKY. This is really coming from just calculating susceptibility. We're kind of agnostic.
You don't have oscillations. So
There are no oscillations. No.
2K effect that
No. No. No.
that's not RKKY, right? That's the picture.
Yeah, so I mean, RKKY just in the sense that you have some itinerant electrons mediating interactions between localized moments. Okay, but you're absolutely right. There are no oscillations. This is a ferromagnetic interaction. Okay, if you strain or move slightly away from charge neutrality, it might actually the pitch might the maximum susceptibility might actually go to finite Q. Actually, Oscar just had a paper showing how this happens in the topological heavy fermion model. Okay, you can get sort of spiral states instead of ferromagnetic states, but it's not related to any 2kF of anything. Yeah.
Okay. We had a lot of questions for this wonderful talk. Any other questions? If not, let's thank Erez again. And this